with the practice session for week 2. So I'm going to give a recap of all the all the lectures you've learned for this week. So starting with the testing and characterization. So we've gone through the definition of testing and characterization, then different types of testing and their importance, and so some of them are described here. And then we have gone through in detail of particular testing. So for example, physical testing, which we've learned for like 2 3 lectures, and so in-depth uh, importance of that. And then the environmental testing and statistics also a little bit. So I'm going to give a brief recap of all these things, all these topics. So starting with the characterization. So characterization, it is a broad term, but it is used for the material's structure and property. So if we want to know about the material's functionalities or properties, then the the broad term is called characterization, and testing is one of a domain uh, in the one of the subset of this domain called characterization. So testing is a particular uh, checking of a particular physical property or chemical property, something like that. So it can vary from material to material, and what property you want to check in the material. I'm going to on the laser pointer. Yeah. So testing is a subset of characterization. So then there are different methods or different characterization techniques. For example, chemical methods, then spectroscopic methods, physical testing methods, dynamic testing methods, then thermal behavior, morphological analysis, and environmental testing. So these are the few techniques which can be used to know the property of a material, or also if we want to know the functionality is present or the structure of the material, that can also be uh, determined using some of these techniques. So first of all, the importance of chemical analysis. So I'm just going to give a brief about chemical testing. So there are different types of testing for chemical testing, basically for a polymer. So these are used to know about the product, as how it will behave, or to predict the product's behavior in a certain condition. So these includes ignition test, pyrolysis, then heating with acid or solvent extraction, then elemental analysis, and some other special tests. So these are some of the tests with which uh, we can determine the property of a polymer uh, when we when it is in a certain condition or environment. And also if you want to know the elemental analysis, then that also we can do using XPS or some other characterization techniques. So I'm going to describe about the physical testing processes. So that is what we have discussed in detail in this week. So first of all, the preparation of the sample, and then its testing. So physical testings are a wide range of testings are there. So but first we need to prepare a sample for that. So how to prepare the sample? So the common technique is the compression molding. So what happens in the compression molding? We have a die here. So and the material is kept inside this cavity of the another die. So this is the moving die, and this is a stationary die. The lower one is the stationary die, and the upper one is the moving die. So and the material is filled in the cavity, and then the top plate is pressed over this material so that it takes the form of a cavity. And that is how we can prepare multiple different dimension of specimens or basically samples. So we call it specimens because they have a particular dimension, specific dimension, which are ISO certified and other basic certified techniques. So these are used for the these specimens are then used to test the particular testing which we want to perform. So there are multiple testing. For example, if we want to perform a testing or compression on the material, then we use a this is a common UTM machine. So this is used to perform the tensile and compressive or shear also can be performed on this machine. So these tests, if we want to perform, then we have to have a specimen of a particular dimension. Then only we can get the standard data. Otherwise, the actual property won't be known. Then, for polymers, we have a curing characteristic also. So that is the curing characteristic is the time at which the 90% of the polymer is getting cured. So if you see the yellow curve, so here the with time the curing characteristic here that is the surface tension, I think. So this is how it goes when this is at 50% curing, for example. So it is with temperature. So this is the maximum temperature at which 90% cure is done and with respect to time. And then we have so I've already told about the tensile, compressive and shear testing. So I'll talk about the universal testing machine first. So this is a machine with which we can determine tensile strength, compressive strength, elongation at a break, or tear strength. So a common specimen is a dumbbell test piece. So here, as I've showed, these are standard specimens. So these few are dumbbell shapes. So these shapes are used. This dumbbell shaped specimen is used for the UTM because uh, we want to hold the specimen from two sides. So that's why the area here is enlarged, and the effective region is this one. So it has a lower dia, and so that the effect of this dia don't come in this region, and we can get a proper testing of this, so proper values we can get. So these are the different uh, uh, different types. So basically, depending on the length of the dumbbell, we have different types of specimen which are standard. So these are some of the standard flanges. So this is a standard specimen for a UTM machine. Then, so this curve I have described in the last class also. So this is a stress strain curve for a ductile material. So as we know that as we increase the stress, the material will get elongated. So this is how we plot the as we increase the force, the elongation will happen. So this curve is basically stress versus strain, but we can also see it as force versus elongation. And at first uh, the curve will be linear, so it will follow the Hooke's law that says that stress is directly proportional to strain, and when we remove the proportionality constant, we get a elastic modulus, the constant which is called elastic modulus. Uh, yeah. So if we take a slope of this linear region, then we have a if we take a slope, we get E is equals to stress divided by strain. that is this region is following the Hooke's law. So here the Young's modulus we can calculate, uh, and then after that, sorry, yes, yeah, yeah, uh, yeah, you can't see that. Oh, okay, I'm so sorry. Uh, yeah, so I think now it is visible. Yeah. So the linear region is where we get the slope, and here the Hooke law will be applicable. So the Young's modulus can be determined using by finding out the slope of this line. So we can get the Young's modulus value for the particular material. Then so up to this is the proportional limit. After that, the curve will no longer be linear. So now after a certain point we get a yield point, but which is where the deformation starts to happen. So at this point the deformation will start. Then after certain point we get a ultimate strength, that is the necking region. So you can imagine the specimen was like this, and it is getting elongated, and after some time the necking will happen. So at this point, this we call this ultimate strength, and then after some point after applying more force, the fracture will happen. So this is a fracture point. And I would like to mention that if the curve is going downwards, because this is the engineering stress we are taking, but if we take a true stress or true strength, the curve will go upwards. I hope you know about the engineering stress or engineering strength and true stress and true strength. You know about the difference between the two, right? Uh, can anyone tell me what is the difference? Hello. Can anyone tell me what is the difference between true stress or true strength and engineering stress or engineering strength? Okay, so let me explain. Yeah, yeah, you can continue. Yeah. Uh, I think you just said the opposite things. So true stress means, yeah, yeah, reverse. So true stress means the force divided by the instantaneous area. That means the area at which, so after, so suppose this is the specimen. So the original area will be this much, but since we are elongating it, so the area is decreasing. So this will be the instantaneous area. So that will be lesser, right? So stress is equals to, sorry, stress is equals to force divided by the instantaneous area. So if the area is lesser, that means the stress value will be higher, because it is the area is in the denominator, right? So the stress value will be higher. That means the curve will be going towards upwards. So it is like that. So this is the true stress, and the engineering stress will come downside. So it will be lower. So that is how the graph is plotted. So basically, generally we take it as engineering stress only. But so if we want to plot true stress curve, then it will go upward. And at this point, and the necking will happen, and in the opposite direction, the area between the region between the yield point and the ultimate strength, there the strain hardening will happen. And I would like to mention that for a ductile material, the fracture will be So it will result in a necking, and then ultimately the fracture will happen. But if we have a brittle material, then the fracture will, so there will be no deformation, only fracture will happen. So crack generation and then a fracture. So there won't be any deformation of the area. So that is the difference between the ductile fracture and the brittle fracture. And I've also plotted it in the last class. So it will be like this. So for a ductile material, it will go like this, and for a brittle material, it won't go any deformation. So it will be like this. So at this region, it will break basically without any deformation. Then we have compression testing. So compression is again, uh, it's basically in the same uh, machine we can have compression also. So as the name suggests, we are compressing the specimen. So we have so initially the specimen will be having some area, and then after compression the area will be increased and bulging will happen. So bulging will start happening. So that is what we can plot. So first in the elastic region we have a linear curve, and after that in the plastic region the curve will be non-linear. So so it signifies that this is the elastic deformation, and then there will be plastic deformation. So elastic deformation will be what is that if we remove the load, then the material will again come to the same place. But in the plastic deformation, if we remove, even if we remove the load, the material will not come on the same place, and the deformation will be permanent. So that is the compression test. Then we have shear test. So shearing means uh, application of force in a region of perpendicular region. So here the force was normal to the specimen, but here the force is not normal, it is in a perpendicular direction. So this is so there are certain different types of shear test. I think I hope you are able to see my slides. I'm changing the slides. So yeah, so first one is the single lab. Oh, okay, I think there is some problem. Yeah, I'll reshare the slide. There is some issue. Yeah. So I've talked about the compression test. I'll again repeat it. So compression test is similar to tensile but in the opposite direction. So we are compressing the specimen here, and we are getting plastic deformation in a form of bulging. So first at a certain point the elastic deformation will happen. That is, the deformation will be linear, and the load versus elongation or compression will be linear, and then after a certain point the curve will not be linear and the plastic deformation will happen. And for shear test, so this is in this the force is applied perpendicular to the specimen, and we have different kind of shear tests. So single lap or double lap, then butt lap, or beveled or joggle. So there are, as you can see in the figure, there are different types of shear tests. Then we have tear test. So like it is like a tearing of the material. So we have a standard specimen in the form of this shape. So this is the standard specimen, and we apply load from both the sides. So here is a notch and it will act as a stress concentration site. So with because of that the crack will initiate and then the material will fail eventually. So that is how the tear test will take place. You can see my slides right now. Like I'm on the tear test slide. Can anyone of you confirm? Oh, still okay. I'll again. Yeah, I'll just share the entire screen. That will be easier. Yes. Actually, the recording of this session will be available, so you can go through that. It will be uploaded on the NPTEL site. I don't upload it, but I will provide the link to the concerned team, and then the team will upload it. So you can get from there. You can get the link from there. Yeah, so here is the tear test. So here we have a particular specimen in the form of, as you can see here. So we have a notch here, and then uh, as we apply the force, the stress will be concentrated in the region of the notch here, and ultimately, so it will start the crack initiation, and ultimately, upon application of load, it will get torn or basically fracture will happen. And so there are multiple kind of specimens. So one is this one, and then we have this one also. So in both this on both these legs we can apply the force, and then the material will turn off. Then we have hardness test. So it is a again a surface property. So both all these were bulk property, but now hardness is a surface property. So it is the deformation of the surface, plastic deformation on the surface. So we have different kind of indenters for this, and different kind of tests are there. So for example, Brinell test, it will it will so Brinell test we perform using a circular or ball indenter. Then we have Vickers that uses a diamond pyramid, which has a particular dimension and angle. Then Noop test, that is again a diamond pyramid, but the dimension will be different as compared to the Vickers. And then we have Rockwell. Again, there are different ranges. So A, C, D will be having diamond cone, and then B, F, G will be having steel ball of a particular diameter, and E will be having steel ball of another diameter, different diameter. So that is how we have different kinds of hardness tests, and also the load will be different for those, and the hardness number will be calculated using a different formula. And so every time if we want to mention the hardness, we generally write it as a Brinell hardness or Rockwell hardness. So because for other so for every indenter, the hardness number will differ. So that is how it is calculated. And so we have some other tests also, shore A, shore D test. So this also so it is covered in the lecture. So I'm not going in depth with that. So these are some of the different types of hardness tests uh, available for the materials. Then we have impact test. So impact is the sudden load. It is basically sudden load on a particular material. So uh, so that is used for the determination of impact strength of the material. So here is a typical schematic of a typical impact tester. So we have a specimen here at the center, which is half in the support and half here. So and the hammer will be blown over here. So this will damage the specimen, and then we can calculate at what load and what uh, at what how many loads, after how many load hammer it is getting distorted or fractured. So we have so basically we have two types of impact tests, ISOD and CHARPY. So this one is the ISOD. We have a notch here and then the force is applied from here. So ISOD can be of three types here, as you can see here. So notched ISOD and then reverse notched ISOD and unnotched. So these are the three types of ISOD tests. And then we have CHARPY. So CHARPY can be unnotched and then notched test. So it is held from two sides and the force is applied at the center. And for the ISOD, the specimen is held from one side and the load is applied on the other end. Then we have abrasion test. So it is basically the abrasion means wearing of the material or removal of the material from the surface. So this is again a surface property, and so there are different types of abrasion tests. So depending upon the arrangement of the abrasion tests. Just a second. Just a minute. Yeah. So depending upon the arrangement of the abrasion test, abradent, we have different types of uh, abrasion tests. So, for example, a reciprocating abrasion. So the material, this is the material, for example. Just turn on the pointer. So suppose this is the material and this is the abradent. So the material specimen is moving in a reciprocating direction on this, and the volume loss or the amount of wear from the surface we can calculate using by weighing the material or by knowing the volume loss. We can test the abrasion property. Then we have the acron type. So in this, the specimen is in a rolled form and the abradant is also a roller, and both of them move in the direction, in a particular direction, and then we can calculate the amount of wear happening from the surface. Same with the table type, but here one abrading wheel is shown here and the test piece is like that. So from the surface again the abrasion is taking place or wearing is taking place. And then we have shifter type. So the test piece is rotating in the particular direction and abrasion is moving in the opposite direction, and that is how the abrasion is taking place. Again the volume loss will be calculated after abrasion. So that is how we know if a material is having what kind of how much abrasion is happening. So that is how we can calculate. Then we have viscosity. So viscosity is a property of material. Basically, it is again it is a property for liquids basically, and solid don't have viscosity. So so liquids, so in between two layers of liquid, we have a shear stress because the liquid is flowing. So for example, these are like here, if I make a diagram, so these are different layers of fluid, and the fluid is flowing in this direction, and so it is flowing with a certain velocity, that is u, and it is having a thickness, that is y. So in this direction, the material is flowing in this direction, and if so here the velocity will be zero because the, for example, suppose the liquid is at rest here and slowly it is moving. So the layer which is attached to the surface, suppose this is the surface, then the layer attached to this surface will be stationary, it won't move, and slowly the velocity will increase. So it will be in a curve, and the gradient will be given as du by dy. So according to the Newton's law of viscosity, the stress will be equal to or directly proportional to the velocity gradient. And if we remove the proportionality sign, we have the viscosity. So here we have viscosity, which is mu, or uh, we can also represent it as eta, that is this sign. So here we have represented dynamic viscosity as eta, and then we have tau, that is shear stress, and du by dy is the rate of shear deformation or velocity gradient. And so for a liquid, we have relative viscosity, which is the viscosity of a material divided by the viscosity of the reference material. So here for polymers, we take the eta is solution viscosity and eta naught is the solvent viscosity. So that will be the relative viscosity of the material. Then specific viscosity is the relative viscosity minus 1. So that is how we can calculate the specific viscosity. Then inherent viscosity, again the log of relative viscosity divided by the constant. Then reduced viscosity, again specific viscosity divided by C. Then intrinsic viscosity, uh, again here the C tends to 0. So it is similar to the reduced viscosity, but for intrinsic the C tends to 0. Then absolute viscosity, so the relative viscosity into viscosity of solvent is the absolute viscosity, and kinematic viscosity is the dynamic viscosity divided by density. So that is how we have different formula for calculating viscosities. Then we have set. So if we want to check that at what time the material the polymer is getting set, and of what thickness, so that we can check using the set testing, that is compression set. So first of all, so there will be the thickness of the test piece, that is T naught. Then we have, so this is the initial thickness, and then we have the compressed thickness, and then there will be a recovered thickness. So for example, our uh, our polymer material will be having a thickness like this. So this will be the initial thickness here, and if I want to compress it, so the thickness will be lesser. Then again, if I remove the press, then again it will get recovered. So this will be the recovered thickness here. So the compression set can be calculated using the formula T naught minus TR divided by T naught minus TS into 100. So that is how we can calculate the compression set. Then we have fracture test. So here we can check using 3-point bending test or 4-point bending test. So this is the material in between, and we have it is attached on 2 points here, and the load is applied at the middle of these two, and it is having a cross section of B into T. So if we want to calculate the fractional stress, so it can be calculated using this formula. Here X is the point at which we are applying the force. So here X will be L by 2 basically, and F is the force which is getting applied, and L is the total span of this polymer material. So here it will be L by 2 plus L by 2, which is L. We are not taking the whole length, but only taking the length from here to here, because these are our point of concern. So this is the point of contact for this, and at the middle the force is applied. Then B and H are the width and height of the specimen. Width and thickness, sorry. Width and thickness of the specimen. And we have the 4-point bending also. Here the load is applied at 2 points, and uh, it is the point of contact at the bottom is 2 at 2 points, and the load is applied at 2 points, so 4 points. That is how we can call, that's why we call it 4 point. Then we have adhesion tests. So adhesion tests can be of multiple types. For example, peel test, then loop tag and rolling back tag. Yeah. So adhesion tests are of three types: peel test, then loop tag and rolling back tag. So peel test again have multiple variations. So first one is the 180-degree peel angle. So these are so this, here it is uh, I think this will be this will be moved in this direction, and then we can check the peel from here, like on the application of how much force the peel will start to happen. Then 90-degree peel angle. So here it is moving in this direction, and we can check at what force the peel is starting. Then T peel. So here it is in a form of T, and again in both the die will move on both sides, and the peel force will be checked. Then we have floating roller peel. So here it will be rolling, and then we can, so suppose this is rolling in this direction and this is rolling in this direction. So we can check the amount of force it is requiring uh, to detach basically. So this is the adhesion test. Then loop tag and rolling back tag are again some of different kinds for the same, to determine the same property. Then we have electrical and thermal conductivity. So electrical and thermal conductivity can be measured using the same process, like 2 point probe and 4 point probe. So 2 point means the connection is set between at the 2 points, and the voltage and current both are applied in between the 2 points. So for example, if we apply the voltage here, the current will flow in between two. But in the 4 point probe, there are 4 points, and the at 2 points we are applying the current, and at 2 point the voltage generation will can be checked, or vice versa. We can apply the voltage and current generation can be checked. And using the formula, these two formula, we can check the resistivity of our material. Did anyone? Yeah. So this is the formula for the resistivity measurement of the sample. So resistivity is defined is resistivity is shown as represented as rho, as shown here. And for 2 point probe, the formula is rho equals to R WT by L. So R is the resistance, W is the width, and T is the thickness or height of the material, and L is the length of the material or specimen. So for example, this is our specimen. So this is the L length. So from here to here, the length is L, and then we have a cross section that is sorry, it is straight line. So it has some width and some height or thickness. So W, T, and L are the dimensions of the sample, and R is the resistance which we get from this. Okay, and for 4 probe, we have the formula as shown here, rho equals to V W T by IL. So here voltage and current are known here, and again W, T, and L are the dimension of specimens. These are also known, and that is how we can check the resistivity or measure the resistivity of the material. And we can check surface resistivity or volume resistivity or electrical strength or conductivity using this setup. Then we have dynamic mechanical analyzer, dynamic testing. So this is used to study the deformation of a material over a range of stress, strain, time, and temperature. So here we have four variables basically: stress, strain, time, and temperature. And it is useful for measuring basically viscoelastic property of a material. So for example, if a material is having both the property of a solid and a liquid, then it becomes viscoelastic. So that is so to check the property, both the property for that matter, so we use dynamic mechanical analyzers. So we can check the property over a temperature range or time range. Then we can mainly measure either strain or deformation against applied stress or vice versa. Then mode of experiment can be strain sweep, frequency sweep, or temperature sweep, and the deformation can be of tension, bending, compression, shear, oscillation, rotation, etc. So here is a typical diagram for a dynamic analyzer. How the property can change or vary on as a function of temperature. So if I start with the so here I'll come to the nomenclature, but uh, as you have already read about it, so I'm just going to explain it. So here G dash is the storage modulus. That means the uh, elastic property of the material. So at a lower temperature, suppose the polymer is behaving in a glassy region, that is it's very brittle, and then after the glass transition temperature the material will become elastic. So that is how the normal curve goes like that, and then after some time it starts flowing, so it becomes liquid. So this is the elastic region, and then this is the viscous region, and that's how the viscoelastic property can be checked. So and then we have loss modulus. I am going to talk about it in the later slides. So yeah, so for a dynamic experiment, we have a complex stress. So complex stress is the mixture of elastic stress and viscous stress. So sigma dash is the elastic stress, and sigma double dash is the viscous stress, and it is shown like that. So suppose delta. If you see this diagram, delta here. Suppose this is sigma stress, then sigma star, then sigma dash and sigma double dash. So from here you can see that sigma dash will be sigma star cos delta, and sigma double dash will be sigma star sine delta. If you have any doubt, you can ask in between. Yeah, so then we have modulus. Modulus is the material's resistance to deformation. So we have E star, which is stress or the complex stress divided by strain. Then elastic or storage modulus, E star, E dash is equals to E star into cos theta, cos delta. And the viscous or loss modulus, E double dash is equals to E star into sine delta. Then the loss factor can be calculated using the formula tan delta is equals to E dash divided by E double dash. And then we have the delta can be 0 to 90 degree. So for a viscoelastic material, the delta will be in between 0 to 90 degree, because if the delta is 0, then the material is proper solid. So there will be only elastic response. And if a material is if the delta is 90 degree, then the material is totally liquid or Newtonian liquid. Then the response will be purely viscous. So we have a material which is in between those two. So the delta is in between 0 to 90 degree. So that is the phase angle, it's basically. Then we have linear viscoelastic theory. So that is, so for ideal solid, ideal elastic solid, we have stress and strain, and it goes like this. And at a particular region, it will be linear. That's where we can get the Young's modulus. And if material is totally liquid or viscous liquid, then the stress and strain rate is checked, and then the slope of that will give us the dynamic viscosity. So for a viscoelastic material, the stress will be dependent both on strain and strain rate. So as we know, for solid, the stress is dependent on strain, but for liquid, the stress is dependent on strain rate. So for a viscoelastic, the stress will be dependent on both the stress and strain. And here, this particular part is time independent. So if a material, uh, so if we are checking only the uh, static property, not dynamic, then we will consider only this much part. But if we are checking the dynamic property, then we have to consider this part also, which is time dependent. So the stress will be E, that is Young's modulus, into strain plus the time dependent part, that is eta dot uh, multiplied by strain rate. So delta epsilon by dt. So this is the formula to calculate the stress in a viscoelastic material. Then we can check the viscoelastic property uh, using different kinds of measurements. So for example, creep recovery or step strain, or some other also, like amplitude sweep or frequency sweep, like that. So basically, fluid can be defined as a viscoelastic when it stores a particular energy and transfer it to in a form of a deformation. As so, that is the elastic energy, and in this case, an elastic modulus will also be attributed to a sample. This class of materials show a behavior that is intermediate between liquid and solid. So, for example, if we are checking the creep recovery means a constant force is applied on the material, and the change in the deformation will takes place will be determined with respect to time. So here time will be considered. So uh, this is the sigma is the force or stress which is applied, and the strain is checked over a period of time. So that is the creep test basically. And for solids, the no matter how much how much force will apply, the strain will be uniform. And for liquid, the strain will increase with time, and the viscoelastic material will fall in between the region from solid to liquid. So the viscoelastic material will be having a curve like this. So initially the strain will increase at a higher rate, and then it get decreased, and then after some time the material will start flowing, so the strain will be again constant over a period of time. So that is how the creep test is taking place. Then we have then we have the step strain. So here the strain is constant, and we are checking the decrease in the stress with respect to time. So for solids, it will be constant throughout the time period, and for liquid, it will be actually decreasing very fast for a liquid, because if you are applying a strain, then there will be very minimal of stress in between the layers of the fluid. So the that will decrease very fast, and the material will start flowing. And for viscoelastic material, the uh, initially the stress will be higher, then after some time the stress will decrease, and then the material will start flowing, so the stress will be minimal or zero at a certain point. So that is how we check the using the creep recovery and step strength. The We can check the viscoelastic property. Then we have amplitude sweep. So here this is the log of g dash, that is shear modulus, and then g double dash. So this is the storage shear modulus, and this is the loss shear modulus. So if if we consider the plot between the modulus and the strain, we have for the first for the initial time, we have a g dash more than g double dash. So here it will behave like a solid. So here in this region it is solid, and after a particular time, after crossing this point, we have g double dash more than g single dash. So here we have g double dash more than g single dash, means here the material started flowing. So here it is in a liquid state or fluid state, and in between we have viscoelastic region. So, so here the micro cracks will start forming. So within zone 1, here the zone 1, the when just before this is getting crossed, here just before this region we have micro cracks only. It will occur before the curve's maximum is reached, and therefore we have G star G dash more than G double dash. That is a solid state. And after maximum is reached, the microcracks develops throughout the sample, and the crossover point. After the crossover point, then after that we have G double dash more than G dash. So that is the fluid state or the liquid state. So the liquid starts flowing. Then we have frequency sweep. So we are applying a sinusoidal shear strain, and we are observing the shear stress over a period of time with a phase angle of phi. So here the frequency is changed. So uh, so different types of techniques are there. So this is one of them, and we can check it using a oscillatory measurement, oscillatory type of measurement, and we can set it as a at a particular phase angle, and we can check the property. Then we have environmental testing. So environmental testing are again different types. So salt spray test and chemical and solvent resistance test. So salt spray test is basically for corrosion, to check the corrosion property of the material, and then we have chemical and solvent resistance. So at what uh, so if a material doesn't react with a particular chemical or solvent, then we can, if we want to know that property, then we can check with the chemical or solvent testings. Then fire and flame resistance. So if we want to check the fire resistance property of our polymer or our materials, then we can check the flash point of the material. Then impact and drop. So I've also already mentioned about the impact test. And suppose the material fall down at a certain height, and then a sudden impact will occur and it can fail. So that is another test to check uh, the impact. Yeah, Ms. Katambira has raised hand. Yeah, yeah. So we are yet to talk about the chemical tests. So in this week, basically, we have only talked about the physical test. So chemical test, maybe in the later week we can elaborate, because we have not gone through much about this. But I can check and let you know, like the duration if you are talking about. I can check the duration and let you know in the next class maybe. So yeah, then humidity resistance and UV test also. So there are multiple tests. So suppose here is an example for a particular material which is having a strength of 62 megapascal at room temperature. But if I want to check, so this specimen was dry and tested in air and at room temperature. But if I wanted to check its wet property, so I've submerged it into liquid and then tested in air and at room temperature. The strength was about 51 megapascal. So the strength is was 60% higher when in the dry condition, but in the wet condition the strength decreased. And then in the realistic uh, situation we have a solution, and then it is tested at not at room temperature but at 37 degrees Celsius. So again the property was again the strength was again reduced. So from 62 MPa we have gone to we have come to 33 megapascal. So it's about like around 50% decrease in the strength of the material. So that's why it is very important to check the environmental condition uh, before reporting it, uh, so that we can predict the behavior of the material at a particular condition. And we have microbe resistance also. So suppose if we want to check the biodegradability of the polymer, then in that case the microbe resistance can be uh, microbe basically we can uh, culture in the atmosphere, and then we can keep the polymer there, and then at with time we can check how much the microbes are decomposing, basically decomposing the polymer. Then the from in the last lecture you have learned about the statical analysis of the data. So these are basically very important for the in case of uh, determining the data, or like analyzing the data, because if the data is not analyzed in a proper manner, it can give us errors in the readings, and sometimes we need to neglect uh, the some of the points which are, if the specimen if the machine is not calibrated, for example, then we need to we won't get the proper data. So we need to calibrate the machine also. So in case of a very sophisticated characterization, we need to calibrate the machines. And if we are taking the readings from a tester, then we need to check that the readings are coming accurately or not. So for that case, we do the statistical analysis. So suppose we take 10 measurements, and then we take a average of that. So and then we check the range or deviation also. So that in that case we need to check the mean of the total readings, and then we check the median, like the middle number of the set, and then we check the mode, or the number which is frequently repeated. So that will give us the better idea of how much the value is coming, like how much accurately the data is coming. So that is how need to check the we need to take multiple readings basically. So if I am performing a test, I generally take two or three duplicates or triplicates. So that will be helpful for me to check the to get the data in a proper or accurate manner. So for that case, I'll take like two, three sets, and then different readings, multiple readings in the same set. So like that, we can actually enhance the quality of our data. So median, mode are very basic terms which we have learned from like class 8th or 7th. And so this is a distribution, common with distribution. So this can be either Gaussian distribution or normal distribution. So suppose the data is having a central tendency, then median mode will all come in the same place. But if data is skewed, or it is not it is shifted from the origin, then we have mode here, then median will be in between the mean, so it will come like that if it is skewed. So then we have deviation or variance. These are also very common terms. So variance is a measure of how far the value of the set are from the mean or the average. So the variability of the data, and the average of the squared deviation is the population variance. So we can calculate it using the formula sigma square, that is the population variance, and s square is the sample variance. So this formula we can use. Sigma square is equals to summation of xi minus x bar. X bar is the mean, and xi is the instantaneous value divided by n, the total number of observations. So that is how we can calculate the variance, population variance, and similarly sample variance also we can calculate. Here this formula is little bit different. In the denominator we have n minus 1. And so that's how we can calculate the sample variance. And then we have standard deviation, which is the square root of the variance. So here sigma is equals to population standard variation and S is the sample standard variation. And it is square root of the variance, that is sigma square, square root of sigma square is sigma. So again the formula is known, and same thing, we can just put a square root and we can get the value for population standard deviation and sample standard deviation. Then we have confidence interval. That means how much the reading can be accurately coming in the region. So for example, if I say I have 95% confidence in my data, that means the data will come in this range. The probability will be 95% of the data will come in this range. And if I say I have confidence of 99.7%, so it will come in this whole range. And if the confidence is 68%, so it will come in only this range. So that is how the confidence interval tells how much confidence we have to get the data in a particular range. Then we have skewness, that is the deviation from the mean. So skewness, if it is positive skewness, it will shift towards left. If it is negative skewness, it will shift towards right. And this is the symmetrical distribution. So deviation from the mean is the skewness. So if the more number of readings are coming in this region, then it will be positive skewness, and if it is coming in this region, then it is negative skewness. Then kurtosis is the so basically all positive kurtosis, negative kurtosis, everything comes at the so the frequency, basically frequency, if so this is suppose the uh, original data distribution as it should be, but the data is coming, so frequency is higher, then it will be in the side of positive kurtosis. If the frequency is lower, then it will be negative kurtosis. So that is how we define kurtosis. So here the frequency, if it is higher, then positive kurtosis, and if it is lower, then negative kurtosis. Then we have correlation and regression. So correlation, it is so to uh, basically it is used to check the relation between two variables. So suppose x is a variable and y is a variable, and we have data coming like this. So I can say that broadly I can say that x is directly proportional to y, but to get a particular relation, I have to check the linear regression. So here, if I predict that it is coming in a linear fashion, then regression analysis has to be done. But here, if I just take, it is just a broad interpretation that x can be directly proportional to y. So here it is description. The purpose is description, just to describe. And if I want to predict, then I have to take linear regression. So here the prediction will take place. So suppose if I want to check that at particular x equals to 1, if I have y equals to 1, then I can predict that at some x equals to 100, suppose, then y will also come as 100. So if I want to predict the data, then I take the linear regression. And if I just want to describe the relation between two variables, then I just do a correlation study. So here statically, if I can just say r, and here we have to check r square. So sometimes r square, so the more the r square value, it should be near 1. So r square value should always be near to 1. So around 0.99 or 0.95, r square value will be considered as a good regression or fit, linear fit, or whatever fit we want to check. If r square value is near to 1 or close to 1, we can say it is a good fit. So here variables are paired. So only two variables are there. But in the linear regression, we have two, three, or more number of variables. And here variables, in the variables, no differentiation between the variables. And in the linear regression, we have one or more independent axes, and one dependent is, that means y is a function of x. So here one is dependent on the other, but here both are independent, and we are trying to correlate them. Then the fits a line through the data. So here implicit fit and here explicit fit. So here we have to define how, in what fashion it is fitting. But here we don't need to fit as such. We just need to broadly define the relation. So here cause and effect does not address, but here we have to show that if x is this much, then y is coming this much. So or y is y is dependent on x. So that is how we need to show it is linearly dependent, or in whatever manner we want to, like the data is coming, we can predict. So that is how we can check the cause and effect. So in the correlation, we cannot check the cause and effect, but we just describe the relation between the two variables. And in the linear regression, we check the cause and effect. We can predict the values, how it will be coming. So now I'll be talking about a few of the questions. So these are some old assignments I'm taking. So you can answer, you can unmute yourself and answer if you know the answer. So which one of the following is considered as environmental testing? Differential scanning, calorimetry, salt spray test, dynamic mechanical analysis, or all of the above? Can anyone tell me? Can anyone? Yeah. So differential scanning calorimetry is the thermal analysis technique, and salt spray test is the environmental testing. Then again, dynamic mechanical analysis is the physical testing. So here the salt spray test is the correct answer, and all of above cannot be the answer. Then we have we can match the following. So I've already told about the viscosity and formula of viscosity. So can anyone tell me what will be the inherent viscosity formula, if they know? Okay, can we can again go through that. So we had relative viscosity. So that was the viscosity of solvent divided by the viscosity of uh, solution. Solution divided by solvent. So this was the relative. Then we had a specific viscosity, eta Sp divided is equals to eta R minus 1. So specific will be this one, B. The If I put the value here, so eta divided by eta naught minus 1. So I will get, upon multiplication, eta minus eta naught divided by eta naught. So this will be B. So second is matched to B. And we can calculate inherent viscosity also. So this inherent viscosity is the log of relative viscosity divided by the C. Then we have intrinsic viscosity. Intrinsic means C is tending to 0. So it is same, this one. And then we have reduced viscosity. So reduced means eta relative minus 1 divided by C. So if I match it, the inherent viscosity is C. So first C is the first option. Anyone have doubt in this one can ask. So specific viscosity is the viscosity in reference to a particular material. So for example, in generally in fluid mechanics, what we take viscosity of oil if I want to check. So viscosity, dynamic viscosity of oil is 900, suppose 900, and the kg per meter cube. And for water, if I want to check in reference to with respect to water, so the viscosity of water is 1000 kg per meter cube, right? So if I want to check the specific viscosity, it is the uh, it is a ratio of viscosity of oil divided by viscosity of water. So if I want to check 900 divided by 1000, it will come as point 0.9. So that is the specific viscosity. I hope you understood. Yeah, so inherent viscosity, uh, basically it is also related to with respect to the solvent. So in case of polymer, we take it not with respect to water, but we take it with respect to solution and solvent. So here if I want to check the relative viscosity, it is the ratio of solvent to solution, solution to solvent. I'm just getting confused in these two. I can go back to yeah. I can go back to that slides where I talked about the viscosity. So the eta was the solution viscosity and eta naught was the solvent. So solution to solvent. So it is the ratio of the viscosity of solution to solvent. And inherent is the again the log of relative viscosity divided by a constant. Okay. Yeah. Then we have compliance. Can anyone tell me what is compliance? Yeah. Yeah. So Young's modulus is stress divided by strength. So compliance will be inverse of that. So compliance we generally denote as D if we are talking about tensile, and uh, if it is shear, then it is J. It is denoted by J, 1 by J. So compliance is equals to strain divided by stress. So the option B is the correct answer. Then which one of the following statement is true? Storage modulus represent viscous component. Loss modulus represent elastic component. Storage modulus represent elastic component, or none of the above. Anyone tell me? So basically, I can just write the modulus. For example, if I'm talking the elastic modulus, E star will be equal to E dash plus okay, yeah. So so E dash will be the storage modulus. So for those who have not understood, I'll just explain. E dash is the storage modulus. Yes. Okay. Yeah. Yeah. Actually, in the damped system, the energy is getting stored in the with the spring, and if it is undamped, then it will keep on releasing this energy. Yeah, I understood your question. So basically, if we have a spring mass system here, this is the spring and it is attached with a mass, right? So if I am pulling it, then it will go to towards this because a spring will resist the action and it will move towards opposite direction if when I release the mass, and then it will again come downward because of gravity, and it will be going through to fourth from this mean position. Okay, but if I put a damper in between, so now the damper will be like this. This is the damper which is having some fluid. So the fluid is something is there, and then we have a spring attached and a mass. So this is the initial position, and if I pull it in the downward direction, then it will try to go upward, but after it won't move much from the mean position because a damper is there. So this is resisting uh, the movement of the mass because it is storing the energy. So storage modulus. So this is a complex system. I can show you in a simpler form. So here is a ball. Okay, I'm throwing a ball on the ground. This is the ground, and I am throwing the ball here, and it will come back, but it won't come back on the same height. This is the original height, but it is coming till here. So this much is the energy stored, and this is the loss of energy. So if I say this is mgh1 and mgh2, so the mgh1 minus h2 will be the energy that is lost. Uh, are you able to understand? Yeah. Oh, okay. Yeah. Yeah. I just wanted to show it. Like, yeah, it should be connected to parallel. Yeah, yeah, yeah. So, yeah, here I made a mistake. Here you can connect it in a parallel manner. Here, you're right, and that is how it will resist the motion. Right. This is wrong. Okay. So the complex modulus is written like this. Coming to the question, it is written like this, and E star is equals to E dash plus E double dash. So E dash is the storage modulus, and E double dash is the loss modulus. Sorry for my writing, it is very bad. So storage modulus is the represents the elastic component. Uh, if I go back to that slide, yeah, here. So E dash is the elastic or storage modulus, and E double dash is the viscous or loss modulus. So from that we can say that storage modulus represents the elastic component. So option C is the correct one. So now, yeah, yeah. Okay. So basically, this is it's a property of a material. So if you want to make a spring using that material, then it makes sense. But if you want to make a system like that, then I don't think it is possible because the damper is a different system and spring is a different system. So I think both of them are two different materials. So in the case of a spring, you have to have a stiffness also. Only this viscous and elastic component won't help, because in mostly in the case of spring we consider stiffness, not the viscosity or elasticity. So I don't think that. Sorry. Yeah. 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 So basically, we have bearings for that reason. Like, if we want to the isolate two structures, suppose the ground structure and the upper structure. So suppose there are vibration at the ground, and we don't want the vibration to transfer to the upper structure. Then we have a the connection will be in the form of a bearing, and at that place we apply bearing, or we put bearing, or like spherical bearing or something like that, so that the vibration transfer won't happen. So it is not necessary to always put a spring or damper system. In that case we can put bearing also, so that it can not transfer the vibration, or friction will not happen. So in designing a material like that, I don't think it is possible with this, because there are other properties also, as I've said. So that is what I think, but I'm not sure if I'm correct or not. Yeah. 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 Yes. Okay. Okay. Yeah. So coming to the next question. So here three circles are there. So the first one is having uh, points in the middle circle, middle region, and then in the second one, the points are there, but in the outer region, but the point are uh, at the same place basically. And in the third region, the points are scattered all over. So can anyone tell me which one is accurate and precise, and which one is accurate but not accurate but precise, and which one is neither accurate nor precise? Yeah. Okay, I'm afraid it is wrong. Uh, Anyone else can guess? Like, yeah, okay, okay. I will not go with that. I'll explain. So the first one is accurate and precise. Accurate means it it is near to the true value. Okay, so it is accurate. But precision means the same value is coming again and again. So here it is both accurate and precise, and the C part is neither accurate nor precise. But in the B figure, we we are not. This is not accurate, because the true value is this, and it is far from true value. But it is precise, because again and again that value is coming. So the option will be A. So B is not accurate, but it is precise. So uh, option C is not correct, but option A is correct. Did you understand my point? Or I understood? Got it? Okay. So yeah, so accuracy means near to the true value. So if a value is coming to the in the center, the true value is the center, right? So if the data is coming near to the center, the point is coming near to the center, that means it is accurate. And precise means the same value is coming again and again. So the same point is coming again and again. So it is precise and accurate both. Okay. But in the case of B, the point is very far to the true value. So it is not accurate. But it is precise because it is coming again and again. So that's why the value is not true. That is not accurate, but it is precise. I hope you understood now. Okay. And in the C case, it is neither accurate nor precise. So option A is correct. And anyone have any other query they can ask? I have done with my slides. So if anyone can want to ask anything, they can ask. Okay. Okay. This characterization technique you're saying? Yeah, so most of the techniques are applicable to most of the tests which I have talked about. Those are applicable to all of the materials, like no matter it is steel or it's metal, ceramic, polymer, anything we can apply. So anything can be tested using this. So for example, if I talk about the universal testing machine, it is basically used for metal testing only. So we make specimens like this. So these can be formed using steel or any other metal, or for polymer also we can try, and ceramics also. So in the case of ceramics, we have brittle failure, as I have told here. Yeah, as I've showed here. So in case of ceramics, because they are very brittle, so in that case we won't get any deformation, but we will uh, get a failure like this. Like the surface will, the cross section will not get deformed, but the fracture will happen. And in the case of a ductile material, that is a metal or other like polymers also, they get stretched a little bit, they get elongated, and then the necking formation will take place. And then so that so overall these kind of techniques are can be applied to other materials also, not only polymers like metal, ceramics. Any other questions? Yeah. Yeah. Yes, yes. Mhm. Yeah, sure. We can also use Vickers also. Vickers, Brinell, yeah. those are the empirical formulas. We can, I'm not sure if we can apply it for polymers, but those are from certain tests. So they have come to that formula. Yeah, those are empirical formulas basically. But I'm not sure about the polymers. So sorry, I can't answer that question. But overall hardness is a surface property, and we can also check elastic modulus also from that. Like yeah, we can get a if I want to perform a nano indentation test, if I perform, I can still get a stress versus strain curve, and the hardness value also I can get, and elastic modulus also I can get. So from the stress strain curve, I can calculate the yield stress also for polymers. So I can just draw it for you. Yeah. So for a typical nano indentation test, so it is between a it can be represented force versus elongation, delta. Yeah. So uh, a normal curve will go like this, and then it will come like this. So this is the loading curve, and this is the unloading curve, and this is the maximum force which I want to apply. So suppose I want to apply, if I applied 9,000 millinewton, or mic sorry 9 millinewton, 9,000 micronewton, so or 10,000 to be, yeah. So if I apply 10,000 micronewton or 10 millinewton, the deformation will go like this. So in this region, at this point particularly, and if I unload it, it will come back. So there will be some elastic deformation. So this will be the elastic deformation, this range, and then there will be a plastic deformation in this range. Okay. So from this experiment, I am putting what is happening in the nano indentation test. I am putting a indenter on a surface. Okay, and it will give me a mark on the surface, a mark like this. If it is a pyramidal, suppose it is a pyramidal indenter, I am getting a mark like this. Okay, and this the machine, it will calculate the hardness. It will give me a hardness value, but from this curve I can get the yield stress and also the elastic modulus. So it is related at some point, and also for polymers we can do that. So I think you can get the yield stress for polymers also using this. Yeah, yeah, yeah. Maybe this is the only way. I'm not sure, but we can do that for this. Yeah, yeah. With this, we can definitely get the idea. Anyone else have a question? Yeah, yeah. Please ask. Mhm. Yeah. Sorry. Impact. Sorry. Hardness. Abrasion. Yeah. Yeah, yeah. Where? Mhm. So it is basically the removal of material from the surface. Yeah. Basically, we check the volume of material removed. So yeah, yeah. So suppose okay, I will write it. Yeah, yeah, I am showing. So normally for metals, what we do, we have a uh, ball kind of tribometer. So suppose uh, it is there is a ball, and our material is there, sample is there. Okay, and it is the ball is on top of the sample. I'm not sure if you can understand from this figure. So a circular specimen is there, and the ball is on top of it, and this ball is scratching the surface. I hope you can imagine it. And the RPM and force and everything we can give to the machine. And this is a basically a tribometer. So this ball reciprocates on the surface of this specimen, and then there will be a loss of material from here after some time. So for example, 1 hour if I keep it, then there will be loss of some material. Okay, I hope you understood this much. Yeah. So then what I do, so suppose this is the original surface, and after some point there is a drop from there because the ball was reciprocating on the surface. So I am showing the cross section. Okay, and then I what I do, I will check this with a profilometer. So I will move a profilometer over here, so it will give me a profile of this kind of thing. Okay, and then this will be the area from where the material is getting removed. So I will calculate this area using a profilometer, and then I can convert it into a volume, and then I can check that how much volume is getting how much volume loss I'm getting. And like so that we using this we can calculate the amount of wear happened in 1 hour, suppose for a load of 500 newton. And like I can vary the load also, so that so many variables are there. But yeah, this is the proper technique to calculate the wear actually. Yeah, profilometer. Profilom Yeah, yeah, yeah. Yeah, directly also if we want, if we can measure the weight. But sometimes it happens that the weight loss is very less, and sometimes we don't get the change in the weight because the weighing balance is not that accurate, for not that so sophisticated for this like to to determine the small change in the weight. So for that case we check the this area we calculate, and then there are some calculations I can tell you in the next class. I'm not remembering now, right now, but I've done it. So sometimes we can't actually see the change in the weight, but we can see the change from the profilometer. Yeah, 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 yeah. Actually, yeah. So the weighing balance also have some limit. So in mg, suppose it can weigh in mg, but the volume loss is in micrograms, not in milligrams. Then we are not able to detect any change. The weighing balance will not give us the change because it's in only in the milligram level. It can also only check in the milligram. It has a limit, right? So that's why in that case we check the most of the case we check with the profilometer, but we can also do that using a weighing balance, like we can weigh it and then check. That can also be done. Yeah, 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 exactly. Yeah, yeah. So no, the we have different kind of profilometer, contact type and non-contact type also. So those are very sophisticated basically. So that that is a very accurate way, I'll say. Yeah. Okay. Any other question? Anyone having any question, or else we can disperse? Okay, I think no one is having question, so we can disperse, I guess. Thank you all for joining.